Hello everyone, welcome to my chemistry class. Today I am going to discuss paper 21, 9701, October-November 2023. This is the paper of Cambridge International AS level. Let's start from the paper. The question number 1 is the elements phosphorus, sulfur and chlorine are in period 3 of the periodic table. Table 1.1 is given there, shows some properties of the elements phosphorus to chlorine. The first ionization energy of sulfur is not shown. So this is the table which contains some information about phosphorus, sulfur and chlorine. The first question is the number of electrons in 3p subshell. As we know that we can predict the number of electrons which are present in the different shells and subshells from the periodic table. So phosphorus it is in group 5, sulfur is in group 6, and chlorine is in group 17. So the general electronic configuration for any element which is in the group 5 is NS2 and NP3. So if we add these two numbers, we will get the group number, whereas the sulfur or group 6 elements, NS2 and NP4, this is the general electronic configuration. N represents the principal quantum number or the number of period. Chlorine or group 7 elements, they have the general electronic configuration NS2 and NP5. So 5 plus 2 is 7, 4 plus 2 is 6, and 3 plus 2 5. Now if we want to represent the number of electrons in 3p of phosphorus, as we can see that there are 3 electrons in the p subshell. So 3 electrons in the case of phosphorus, 4 electrons in sulfur, and 5 electrons in chlorine. Then the total number of unpaired electrons. Now the unpaired electrons, if we look at the unpaired electrons, we know that the p subshell contains 3 orbitals. So if we have to arrange the 3 electrons in p orbital, we must show like this. All the electrons must be unpaired. So there are 3 unpaired electrons. If we want to show the 4 electrons, then we have to make a pair. Now, if we make a pair, then there must be 2 unpaired electrons. For the 5 electrons, you have to make another pair. So there is just 1 unpaired electron in p subshell of chlorine. Now, complete the table. We have completed the table. Then construct an equation to represent the first ionization energy of phosphorus. Ionization energy is the minimum amount of energy which is required to remove 1 mole of electron from 1 mole of gaseous atom. So this phosphorus must be the gaseous atom to remove 1 mole of electron. So this is the electron which is removed from the 1 mole of gaseous atom of phosphorus to form 1 mole of gaseous 1 positive cation. So this is the first ionization energy equation for the phosphorus. Now, the possible values for the first ionization energy of sulfur are given. So these are some values. Circle the correct value and then explain your choice. If we look at the graph of the ionization energy of these are the elements of period 3. So the general graph for the ionization energy of period 3 is like that. This is, for example, the sodium, then magnesium, aluminium, and then silicon, phosphorus, then sulfur, and then chlorine and argon. So this is the general representation of the graph of the first ionization energy of period 3 elements. As we can see, there are 2 exceptional cases. Like the general trend of the ionization energy is that it increases from left to right in a period. But there are 2 exceptional cases, like here, this is Mg, this is aluminium. Here we have the phosphorus and sulfur, and then chlorine and argon. And then sodium, and this is sodium, and this is silicon. So these are the elements of period 3. Now, if we look at the ionization energy of sulfur as compared to phosphorus and chlorine, so this is phosphorus, and this is chlorine. So the ionization energy of sulfur is less than both phosphorus and chlorine. So as the phosphorus is 1060, it must be less than 1060, and chlorine definitely it is 1260. It must be less than this number. So if it is less than 1060, it should not be 1160, which is more than this number. So these two answers are incorrect. So this is the answer. The 1000 kJ per mole is the ionization energy of sulfur. Now, the reason, explain your choice by comparing your chosen value to those of phosphorus and chlorine. Uh, as we can see that the proton number of the phosphorus is 15, 16, and 17. So the number of protons which are present in the nucleus of an atom, or the nuclear, if we look at the nuclear charge, the nuclear charge of sulfur is 16, and of chlorine is 17, whereas the phosphorus is 15. So sulfur has less nuclear charge than chlorine, but although it has more nuclear charge than phosphorus, so we can say that the sulfur has less nuclear charge than chlorine. So less attraction with outermost electrons, outermost electrons. So definitely less energy needed to remove electron. Whereas if we compare the phosphorus and sulfur, uh, phosphorus has three electrons in p subshell. All are unpaired, whereas in sulfur there is a paired electron in 3p. So less energy needed due to electron spin repulsion in sulfur. Whereas we can also see that phosphorus, the 3p orbital is half filled. We can also say that in the phosphorus, because the 3p orbitals or 3p subshell is half filled, is half filled, and half filled orbitals are more stable. So this is more stable. Then, so we have to cover almost 4 points. The next question is regarding the electronic configuration. The proton number of phosphorus is 15 because this is the anion. So for P3 negative, it has 18 electrons. So we'll have to distribute 18 electrons, which is 1s2, then 2s2, then 2p6, then 3s2, and then 3p6. So this is the electronic configuration of P3 negative or phosphide ion. State the trend in ionic radius. Now, if we look at our specification or the syllabus, we know that the trend of the cations is like the sodium, then Na positive, Mg2 positive. If the size of Na1 positive is this, then Mg2 positive is comparatively less than this, and then Al3 positive, and then Si4 positive, then P3 negative, S2 negative, and Cl negative. So this is the graph of the ionic radius of period 3 elements or anions. So this is for Na positive, then Mg2 positive, then Al3 positive, then Sa4 positive, P3 negative, S2 negative, and Cl negative. So first of all, we have to explain the trend. As we can see that the anionic size or the ionic radius that decreases, it decreases from P3 negative to Cl negative, decreases from P3 negative to Cl negative. If we look at the number of electrons and the protons, so we can see that here we have the 15 nuclear charge, 16 is the proton number, the 16 nuclear charge, and then 17 protons in the nucleus, so 17 is the nuclear charge. The nuclear charge that increases from left to right. So we can say that the nuclear charge increases. Nuclear charge is the number of protons which are present in the nucleus of an atom. So nuclear charge increases from P3 negative to Cl negative. When nuclear charge increases, as we look at the attractive forces which are present between the nucleus and outermost electrons, so there is an increase in the attraction of the with the outermost electrons. So increase in attraction with outermost electrons. As we can see that the shielding electrons are same, but like P3 negative, then S2 negative, then Cl negative. So the electronic configuration is 2, 8, 5. This is 2, 8, 6, and this is 2, 8, 7. As we can see, the electrons which are lying between the nucleus and outermost shell, they are the 10 electrons. So there are 10 shielding electrons. So we can also make a reference that they have the same shielding electrons. So shielding electron can reduce the attractive forces between the nucleus and the outermost electron. So if these shielding electrons are same as if we move from left to right in a period, the shielding electron remains the same. So this is the reason that the first of all explain in the terms of trend that ionic radius decreases from P3 negative to Cl negative. Then nuclear charge increases as the number of protons are increasing. So greater attraction between the nucleus and outermost electrons. So nuclear attraction will also increase, and the shielding electrons, they will remain constant. There is no change or increase in the shielding electrons. Then the next part is regarding the observations. So a student does 3 tests on samples of sodium chloride, complete table 1.2 with the observations the student makes in each test, adding a few drops of bromine. As we can see that the reaction is between NaCl, sodium chloride, and bromine. Bromine is below chlorine in its group, so bromine is less reactive than chlorine, so there will be no change. So no visible reaction, so no visible change. Okay. Then there is another thing as well, that if we look at the solution of sodium chloride, aqueous solution of sodium chloride, so this is colorless. Then if we add the bromine Pr2, which is brown, so this color change is also acceptable, that we have the colorless aqueous solution of sodium chloride, and if we add bromine brown, so the colorless solution changes to orange or brown or yellow. So all colors are acceptable, brown or orange. So we can also say that colorless to brown or orange. So this color is not due to the chemical change, but there is no reaction. As we can see that this is the color of the bromine. Bromine is brown, orange, or yellow. So we can see the color of the bromine. There is no color change. The solution was colorless, but if we add a colored liquid or a colored substance, that if that is the color of that substance, it means there is no change in the color. That is the color of the bromine. So we can say that no visible change, or colorless to brown. Addition of a few drops of concentrated sulfuric acid. Now, concentrated sulfuric acid, if we add the concentrated sulfuric acid in it, so we know that the concentrated sulfuric acid, it reacts with the sodium chloride to make sodium hydrogen sulfate plus HCl. So addition of few drops of concentrated sodium chloride, the solution, there must be no color change, as we can see that the colorless liquids are there, or colorless solutions are there. So there must be no change because this is happening within the container. This is not happening outside. So that's why the HCl, that although that forms a misty fumes, but here the HCl fumes, they actually dissolve in this aqueous solution to make aqueous solution of hydrochloric acid. So that's why there must be no visible change, no visible reaction. The solution is colorless before the experiment, and it remained colorless at the end of the experiment as well. So addition of a few drops of dilute aqueous silver nitrate. Silver nitrate is generally used to test for the presence of halidine, and the chloride can give us the white precipitates. So we will get a white precipitate, and this silver nitrate can produce a green precipitate with the bromidine, and yellow precipitates with iodine. But here we have the aqueous solution of sodium chloride, which contains chloridine, so we'll get a white precipitate. Okay, so the next part is POCl3 shows similar chemical properties to PCl5. Now, POCl3 has a melting point of 1 degree Celsius and a boiling point of 106. POCl3 reacts vigorously with water, forming misty fumes and an acidic solution. Explain how the information in D suggests the structure and the bonding of POCl3 in simple covalent. Now, as we can see that POCl3, it has a low melting and boiling point. So low melting boiling points mean there must be weak intermolecular forces or the van der Waals forces, which must be present between the molecules of POCl3. And if it has a vigorous reaction with the water, it means that this is the hydrolysis. So the low melting at the boiling point shows that low melting and boiling points suggests weak van der Waals forces between molecules. Weak van der Waals forces between molecules, and the vigorous reaction with the water suggests hydrolysis. Then construct an equation for the reaction of POCl3 with water. So with water, H2O. As we can see that POCl3 is like PCl5. So PCl5, it reacts with the water, form H3PO4 plus HCl, or H3PO3, or it's H3PO4 plus HCl. So this will form the same type of products, that POCl3 plus water. It will give us H3PO4 plus HCl. So if we balance this equation, so there are three chlorines, so we can put three here, and then 3 plus 3 is 6 hydrogen, so 3 here. So this is the balanced chemical equation. Then the next part is regarding dot and cross diagram. Oxygen, we know that it has 6 electrons in its outermost shell. Okay, then the phosphorus, it has 5 electrons. So phosphorus has a lone pair, then 3 bond pair, and chlorine has 3 lone pair and 1 bond pair. So we can start from the chlorine. That chlorine has 7 electrons. So 1, 2, 4, 6, and then 7, 2, 4, 6, and then 7, 2, 4, 6, and then 7. Now, this phosphorus can make definitely single covalent bond with this chlorine. So the phosphorus electrons now 1, 2, 3. Phosphorus has 5 electrons, 3 are busy with the chlorine. So it has 2 more electrons. So the 2 more electron, definitely they can form a double covalent bond with oxygen. So the dot, cross, dot, cross. So these are the electrons of oxygen. You can differentiate the electrons of the oxygen from the chlorine as well. But oxygen has 6 electrons, so 2 are making double covalent bond with the phosphorus. So the rest of the 4 electrons are as well there. So this is the dot and cross diagram. That we can see that the phosphorus and the chlorine, they are bonded through a single covalent bond, but there is a double covalent bond with the oxygen. So this is the structure of POCl3. Now the next part is from the energetics. PuCl3 forms when PCl3 reacts with oxygen. So this is a reaction in which we're getting the PuCl3. The table 1.3 gives some relevant data. So enthalpy change of formation of PCl3 is given. Then enthalpy change of formation of PuCl3 is given, and then the bond energy is given. Okay, so to find enthalpy change of formation, enthalpy change of formation is the enthalpy change when 1 mole of the compound is formed. So the enthalpy change when 1 mole of compound is formed, the compound is formed from its elements under standard conditions. And the elements must be in their standard forms as well. And standard states. Now calculate the bond energy of P double bond O in POCl3 using the data in the table. So the reaction between PCl3 and oxygen is like this, PCl3 plus O2, POCl3. So this is the balanced chemical equation. Then the data regarding enthalpy change of formation. So if we make a Hess-Sisler triangle, so this is the formation, phosphorus and chlorine, they can react to give us PCl3 as we can, if we balance the sequence, so 2 and then 3. So this energy is given. So this is 2 times minus 289. This is the enthalpy change of formation of PCl3. Then the enthalpy change of formation of PuCl3. Now, if we add oxygen here, so the elements like phosphorus, chlorine, and oxygen, they can form POCl3. So this is the enthalpy change of formation of POCl3, which is minus 592. So first of all, let me calculate the enthalpy change of reaction of this specific reaction. So if we consider this. Now, according to the Hess's law, this is one root and this is another root. So this is 2 times minus 289 plus x is equal to minus 592. So x is equal to minus 592 plus 2 times 289. So this value is this is mm, here we have actually 2 moles. So because the two formation of the 2 moles of POCl3 is there, so we can add 2 here. So this is mm, minus 1184 and then plus 578. So the answer is negative 606. Now this is the answer. This is the enthalpy change. I mean the enthalpy change of this reaction is negative 606. Now we have to calculate the bond energy of P double bond O. So we can apply the another formula that delta H enthalpy changes sum of energy which is required to break bonds minus sum of energy which is released during bond formation. So we have the delta H like 606, then bond broken. So these are the bonds. PCl3 has 3 PCl single bonds. So 3 times 2, 6. It means we have 6 PCl bonds. Then we have O double bond O. This is the energy which is required to break bonds minus the structure of POCl3 that is already done. This has, because 2 is here, so we can say that there are 6 PCl3 bonds. So 6 PCl3 bonds and then 2 P double bond O. As we can see, there are some common bonds. So 6 PCl, 6 PCl. Now we can cancel these bonds. So negative 606 is equal to O double bond O. This is the broken minus 6, sorry, 2. Yeah, 2p double bond O. So this is 2p double bond O. We have the value of O double bond O, which is in the table, I think. Yes, this is 496. So minus 606 is equal to 496 minus 2p double bond O. So 2p double bond O is 606 plus 496, and which is 1102, because we have to calculate the bond energy of P double bond O. So there are 2 P double bonds, so we can divide in 2. So it is 551. So this is the bond energy of P double bond O. So we can uh, solve this question in 2 steps. First of all, calculate the enthalpy change of this reaction, and then you can apply the another formula. Enthalpy change is equal to sum of bond broken minus bond formed, in which you can calculate the bond energy of P double bond O. Now look at the next part. This is another question. So this is the reaction between barium oxide and water. We'll get barium hydroxide, and then in reaction to barium carbonate plus water, then this is the reaction of base with acid to form A plus water. So let's start from this part. State the variation in the solubility of group 2 hydroxide. Uh, the group 2 hydroxide solubility that increases down the group. Increases down the group. So there are the students will have to remember the solubility of hydroxide and sulfates in their syllabus. So just remember from these two compounds, barium hydroxide and barium sulfate. So barium hydroxide is aqueous. This is alkali, and barium sulfate is a white precipitate. So if we look at the solubility of hydroxide, because barium aqueous solution of barium hydroxide is alkali, so that's why the solubility of hydroxide increases. And what about the solubility of the sulfate? Barium sulfate is a white precipitate, so that's why the solubility decreases. Just remember the trend. The reasons are not required at this level. The reasons are in A2. So just remember the trend that the solubility of the hydroxide that increases down the group and sulfate decreases. State what is observed in reaction 1. So just think about the reaction 1. So reaction 1, we are dissolving the solid barium oxide in water. As we are getting the alkali, so that's why barium oxide dissolves or disappears. So this white solid disappears. So just reactant for the reaction 2. Uh, we're getting the barium. Okay, we are getting the barium carbonate from barium hydroxide, and we are getting the water as well. So barium carbonate and water. So it means that if it reacts with the carbon dioxide, we can get the barium carbonate and water. So this reacts with carbon dioxide. So carbon dioxide is a reagent. Just like the test of the carbon dioxide, we know that the carbon dioxide turns lime water milky. So lime water is this, like calcium hydroxide is a lime water, then carbon dioxide, then we will get a calcium carbonate and water. So this is the reaction, just like this. Carbon dioxide turns lime water milky. This is the lime water. And if we replace the calcium with the barium, because calcium and barium both are present within the same group, so that's why we'll get the same idea. Identify A. So A is a reaction of this acid with the barium hydroxide. So this is ethanoic acid. This contains CH3COO negative ion and barium Pa2 positive. So if we exchange the numbers without signs, we'll get the formula. So which is barium ethanoate. So this is barium ethanoate. CH3COO 2 times Ba. So barium hydroxide is made by the reaction of barium with water. So going in. So this is barium. If it reacts with water, we will get barium hydroxide and hydrogen. So group 1 and 2 metals are the metal which reacts with the liquid water to get barium hydroxide, and this is hydrogen gas. And if you balance this equation, we'll get a coefficient 2 before the water. So this is the balanced chemical equation of reaction between barium and water. Now there is another question. Now state which compound decomposes first when there is a baryto calcite when this is heated. So this contains two carbonate, barium carbonate and calcium carbonate. So he's talking about thermal stability of group 2 carbonates. So according to your syllabus, the thermal stability of group 2 carbonates and nitrate that increases mean the element which is present below another element in the group 2, that's carbonate, is more stable. More stable mean it requires more temperature to decompose. If we look at the position of these two elements like calcium and barium, so barium is below calcium. So barium carbonate needs more temperature to decompose as compared to calcium carbonate. So which compound decomposes first? If we have a mixture of barium carbonate and calcium carbonate, barium carbonate requires more temperature to decompose. So calcium carbonate, calcium carbonate and barium carbonate, Thermal stability increases down the group. So it means that barium carbonate require more temperature to decompose, but he's asking that which compound decomposes first. So calcium carbonate is less stable, thermally less stable, so that's why calcium carbonate decomposes at first. Calcium carbonate state. And then why? Because thermal stability increases down the group 2. Okay, we can also say thermal stability of carbonates. You can specify this because we're talking about the carbonate at the moment. Now construct an equation for the complete thermal decomposition of this compound. So this contains this, just think about that if we have a calcium carbonate, it decomposes to give calcium oxide plus carbon dioxide. So the barium carbonate decomposes in the same way, barium oxide plus carbon dioxide. So if we decompose this substance, we will get the two oxides like calcium oxide. This is calcium oxide, then the barium oxide. 1 mole from the of carbon dioxide from calcium carbonate and 1 from barium carbonate. So you will get the carbon dioxide, but if you want to balance it, you will get 2 carbon dioxide. Then the next part. So barium hydroxide is used to hydrolyze organic compound. Shows that this is the reaction between V and barium hydroxide followed by acidification. Now this contains two group. This is a cyanide or a nitrile. You can say nitrile. Nitrile is better. And this is the ester. So this part is like this. Now from the acid, if we do the acid hydrolysis, sorry, this part is like this. Okay, if we do the acid hydrolysis, we can say that this carboxylic, this ester part will be converted into carboxylic acid, and we will get alcohol as well. So from this part, we will get CH3, CH3OH, or CH3OH alcohol, and then the rest of the part here, the nitrile is also oxidized to carboxylic acid, and here we'll also get the carboxylic acid. So you will get a structure like here you get a carboxylic acid, and here you will also get carboxylic acid. So 2 carboxylic acid must be there. How? Potassium chlorate is widely used as an oxidizing agent and to make oxygen. So define oxidizing agent. The substance which causes oxidation of the other substance. But reduces itself. So the substance which causes oxidation of the other substance but reduced itself, that is the oxidizing agent. And then potassium chlorate decomposes when heated. MnO2 is a catalyst. The exothermic decomposition reaction. Complete and label the diagram. Figure 3.1 shows the effect of this. Exothermic decomposition mean that the products must be below the reactants. And if MnO2 is a catalyst, and it will reduce the activation energy. So first of all, if we are doing the decomposition when heated and then MnO2 catalyst is added, So we can show that the reactants are converted into the products without catalyst if this much amount of the energy is the activation energy. This is the activation energy. And if we add the catalyst, catalyst reduces the activation energy. So that's why this will be the activation energy for catalyzed reaction. So this is uncatalyzed reaction. And this one is a catalyzed reaction because catalyst lowers the activation energy. Now, when KClO3 is heated without catalyst, so these are the products, explain why the reaction is described as disproportionate. A disproportionate reaction is that reaction in which the same substance is being oxidized and reduced. So we can check the oxidation state. Now here we have the oxidation state of potassium is +1. Now there are 3 oxygens, so the oxidation state is -2. So -6 plus 1 is -5. So here we have +5. Then here we have the +1. Then 4 times -2. -2 is the oxidation state of oxygen. So -8 is the sum up. Then +1, -8 plus 1, -7. And so +7. And here we have +1, -1. So the oxidation state of potassium +1 on both sides, oxygen -2 on both sides, but the oxidation state of only chlorine, okay, is changing. So we can say that chlorine is both oxidized and reduced. Chlorine is both oxidized and reduced, from +5 to +7 oxidized, and +5 to -1 reduced. So if the same species or the same substance is being oxidized and reduced, then that reaction is disproportionate reaction. Now, this is a reaction in which the molten potassium chlorate reacts with the glucose. So KClO3 melts at 630 at this temperature. Both carbon dioxide and water are gases. Okay, so both carbon dioxide and water are gases. This is a very important point here. Use the ideal gas equation to calculate the volume in meter cube of 1 mole of the gas at 630 is the temperature. And then 1.0 times 10 raised per minus 10 raised per 5. And this is the pressure. So if we apply the general gas equation or the ideal gas equation, which is PV is equal to nRT. So one more, okay. So to calculate the moles, PV over RT. So we can put the values here. Pressure is 1.0 times 10 raised per 5. So pressure is okay, we have to calculate the volume. Yes, if we want to calculate the volume, then we should be nRT over P. So there is 1 mole of the gas. So here 1 mole times R is 8.31 times temperature is 630. And then the pressure is 1.0 times 10 raised by 5. So if we calculate this, it will be 0.0524. So 0.0524 meter cube is the volume of 1 mole of the gas. Now, 5 gram of this, the glucose react completely with the molten KClO3 react completely, it means this is the limiting reagent. So use your answers to D1. D1 is the volume of 1 mole of gas to calculate the total volume of the gas released. Now, according to the equation, there are two gases because the temperature is 630, and the question also has information that the carbon dioxide and water are both gases. So these are gases. We have 12 moles of gases on the right hand side, but just look at the data. We have 5 grams of glucose. So first of all, calculate the moles in glucose. 5.0 divided by 180 is the MR. So 5.0 divided by 180 is 0.0278. Now, if we look at the moles, these are the moles of glucose. So moles of glucose. Glucose is this. So 1 mole is producing 12 moles of gases. Okay, and 1 mole is producing 12 moles of gases. So if we have this much amount, then 1 mole ratio 12 and 0.0278 ratio x. So x is 0.0278 times 12. So these are the moles of gases, which is 0.3336. These are the moles of gases. So total volume of the gas release. Because we are using the same conditions, and we know that the volume of 1 mole of gas under these conditions is 0.0524. So the total volume of gas, this is moles times volume. We cannot use the 24 because we have already calculated the volume of 1 mole of gas under these conditions in meter cube. So time moles times 0.0524. So we have the moles of gases 0.3336 times 0.0524. So if we multiply these two numbers, we'll get 0.017. So we have to use the same data, which is the part of our question. So this is the way to get the volume, total volume of the gases. We have two gases on the right hand side. Don't forget the data completely or informations. The information is that water is also gas. Now, this reaction is okay. The structure of glucose. This is the structure of glucose. So complete table 3.1 and have to identify the number of primary, secondary, and tertiary alcohol. Okay, so primary alcohol is like CH2OH, which has just one link. I mean, this is just one R group is there. Whereas the secondary alcohol, it is CHOH. So we have two more links with the carbon. And tertiary alcohol is COH. We have the 3 links with the carbon or alkyl group. So if we look at this OH, this is CH2OH, which is the primary alcohol. Then this carbon is attached with the 2 carbons. So this is CHOH, which is secondary alcohol. Then this is CHOH, which is also secondary alcohol. This is CHOH. This is also secondary alcohol. Then this is also secondary alcohol. So there is just one primary alcohol. This is CH2OH. This is just one primary alcohol. There is no tertiary alcohol. So 1, 2, 3, 4. There are 4 secondary alcohols. Okay. Separate samples of the aqueous glucose are tested with the reagent shown in the table 3.2. So acidified KMnO4 and warm, then failing reagents and warm, then alkaline I2 and warm. Now, if we look at the acidified KMnO4, that can be used to test the presence of 1 degree or 2 degree alcohol. I mean, primary and secondary alcohol. 3 degree alcohol cannot be tested because that is not further oxidized. So acidified potassium permanganate, if we look at the color of the acidified potassium permanganate is KMnO4 is purple, So when the primary and secondary alcohol are oxidized, the color changes from purple to colorless. Then failing reagent and warm. Failing reagent is used to test the presence of aldehyde. As we can see that there is no aldehyde in our structure. He's talking about this structure, yeah. So there is no aldehyde. There is a carboxylic acid, CH3. There's aldehyde there, yes. So this is aldehyde. So aldehyde, orange precipitate form, failing solution. Yes, this contains the aldehyde. So we will get a orange red precipitate. So this part is aldehyde actually. This part is aldehyde. So that's why the failing solution will give a red precipitate or orange precipitate. So alkaline I2 and warm. Alkaline I2 and warm, that is used to test the presence of methyl ketone, CH3C double bond O, or the alcohol like CH3CHOH. If we look at here, that CH3CHOH, it must be there, or CH3C double bond O, ketone must be there. So there is no ketone, or there is no methyl ketone, CH3CHOH. So CH3, there is no CH3CHOH. So that's why it will give us the negative test of iodoform test. This is the iodoform test. So there will be no reaction, no observation. Then there are many structural isomers, defined structural isomers. The molecules of the compounds which have the same molecular formula but different structural formula, they are the structural isomers. So the molecules with same molecular formula but different structural formula, they are the structural isomers. Let's see the next question. Now we have the compound C and D are alkenes with the same molecular formula. C5H10, mean pentene is there. Now give the systematic name of the D. D. Now in D, if you look at the longest chain, this is the longest chain which contains 1, 2, 3, 4. Mean there are 4 carbon atoms, but the alkene is on the first carbon because alkene must be preferred on this branch. So 1, 2, 3, 4. So we can say this is a but1-ene, but1-ene. The longest chain is but1-ene, but the third carbon that contains a methyl group as well. So the complete name is 3-methyl but1-ene. Explain why C and D do not show geometrical or cis-trans isomerism. For the cis-trans isomerism, there must be 2 conditions. Number 1, there must be a double bond. These 2 compounds contain the double bond. But the double bonded carbon, they must have their different groups. Now, if we look at this double bonded carbon, so this carbon is attached with 2 hydrogens. So 2 same groups are attached. This carbon is attached with 2 CH3 groups. So this carbon is also attached with the 2 same groups. And in D, this carbon is attached with the 2 same group. So the double bonded carbon, C double bond C bond, has the same group attached. So if the same groups are attached on the double bonded carbon, then that alkene will not show the geometrical or cis-trans isomerism. Draw the structure of a molecule that is a positional isomer of C and D. In positional isomer, you have to change the position of double bond or the branch. Now, if we look at the position of like this, okay. So if we change the position of double bond, we can get a structure like this, 1, 2, 3, 4. Okay, if we make here, this is here, it is 2 methyl. Okay, if we put a double bond here like this, now 1, 2, 3, 4. This is 2 methyl but 1-ene. So this is 2 methyl but 1-ene. So in both these structures, okay, D is but 1-ene. So this is but 1-ene. This is but 1-ene. We have, but the D is 3 methyl. This is 2 methyl. So we can change the position of this branch or the position of double bond. So as the double bond is on both positions, mean this is a 1-ene and this is 2-ene, so we can change the position of alkyl group. Give the structural formula of the compound formed when B reacts with hydrogen in the presence of platinum catalyst. D is like this. D is CH3 here, then C here CH3, here CH, then CH double bond CH2. So this is the structure of D. So if we add hydrogen, we can say this is a CH3 2 times, then CH, and then CH2, and then CH3. Because if we add the hydrogen, so hydrogen will be added here or here, and we have to remove the double bond. So this will become CH2, CH3. So this part is CH2, CH3. The rest of the part should be copied. So C can form a addition polymer. Draw the structure of one repeat unit. So C is, okay, C is like this, C double bond C, and then CH3, and again CH3, and then again CH3, and then H. So this is the structure of C. So if we want to make the repeat unit of one addition polymer, just remove the double bond. So the rest of the structure must be copied. So this is the structure, and you have to extend these carbon to make the one repeat unit of this compound. Then now the mass spectrum of C shows a molecular ion peak. This is M peak, and relative intensity is 48.7. The relative intensity of M+1, this is the M+1 peak, show that this information is consistent with the molecular formula of C. Now we can find the number of carbon atom. This formula is used to find the number of carbon atoms in a compound. 100 by 1.1 times percentage or intensity of M+1 peak over percentage or intensity of M peak. So this is 100 divided by 1.1. The percentage or intensity of M+1 peak is, this is M+1 peak, that is 2.7. And the intensity or percentage abundance of M peak is 48.7. So this is N is equal to 5. Okay, now the MR of this compound is 70. So MR of this compound is 70. If the carbon number is 5, so we can say C5 It means that 12 plus 5, which is 60, So if we want to justify the 10 more hydrogen, so it must be like this, because 1 times 10 is 10, and we will get a 70. So C5H10 can be justified by using this formula. How? C and D both react with HBr. C react with HBr to form E, and this is E and this is C. Okay, now complete the diagram. Mechanism. We have to show the mechanism, draw the structure of the organic intermediate, and include the charges, the dipoles, lone pair of electrons, and curly arrows. So charges. So first of all, show the charges. This is partial negative and this is partial positive. Uh, okay, the dipole. Then the curly arrows. Okay, so the attack must be by the double bond. Here, this double bond will attack on the positive hydrogen, partial positive hydrogen atom. Then there must be a hydrolytic chain. Here, two curly arrows. Then if this double bond is broken, you will get a compound. Just copy that compound like this. Okay, and here we have the hydrogen. You can show the hydrogen or you can skip the hydrogen as well. Now here, this is the carbocation. We'll get a positive charge. This is the secondary carbocation. Now Pr negative, which is formed, it has a one lone pair. So you have to show the attack on this positive center. So if you show the attack on this positive center, this bromine is attached here, and you will get a structure like E. Now the the charge, this is the positive charge. These are the dipoles. Then lone pair, this is the lone pair of electron, and the curly arrows. So you have to show the 4 points, the charges, the dipoles, the lone pair of electrons, and arrows. Now D reacts with HBr to produce F, a chiral bromoalkane. Now, if we look at the structure of D, where is D? Okay, this is D. 3-methyl-bute-1-ene is D. 3-methyl-bute-1-ene is D. Okay, this is D. 3-methyl-bute-1-ene is D. So if we react with the hydrogen bromide, first of all, we can say that here this structure will be like this. And this is the structure. If we break the double bond, and if we want to get the chiral bromoalkanes, we should add bromine here. Because in this case, this bromine is attached with the 4 different groups. Now here, CH3, hydrogen, and then the rest of this chain, and then bromine. So this carbon is chiral. So if we want to get the chiral product, that chiral product must be like this. Here was the double bond. So if we remove the double bond, we will get a bromine here. So this carbon is chiral. This carbon is chiral. Then explain why the reaction of HBr with C and D produces different major products. So the major products, the formation of the major product is linked with the Markovnikov rules. Okay, so according to this rule, the major product is what is the major product formed? We have to attach the more electronegative atom with that carbon which contains less number of hydrogen, or hydrogen must be attached with that carbon which has already more hydrogen atoms. But C, because if we look at the C, and if we attach the hydrogen atom, because this carbon contains one hydrogen, so if we attach the hydrogen here and bromine here, so we will get a carbocation here. So this will form, C actually form a here it will form a tertiary carbocation. If we make it like this, so this is the C, and D will form a secondary carbocation. This will form a secondary carbocation. If we attach hydrogen here, then this will form a secondary carbocation. So first of all, we have to mention that C has a tertiary carbocation. Then D has a secondary carbocation. Secondary carbocation. It also has a primary as well. So more alkyl group, if the more alkyl group are attached, they will produce a more inductive effect. So more stable intermediate will be formed. So secondary carbocation is more stable as compared to primary, or so tertiary carbocation is more stable as compared to secondary and primary carbocation. So we can say that the tertiary carbocation provides inductive effect of three alkyl groups, and this is more stable than secondary and primary. Primary carbocation. Then C can be used to form H. Now this is another structure of H. Now this is a ester linkage. This is a ester linkage, C double bond OO. One possible synthesis of H shown in this 4.5 different portions of the C and use the reactions. Okay, let's see the reaction. Now C, if it reacts with the HBr in reaction 1, okay, we'll get this thing, and then this will react to form another J, and then this reaction G plus this. Okay, so if we are reacting the C with the different material like this, now this reaction HBr, reaction 1, we are getting Br here. So halogen alkanes are actually attached here. Halogen alkanes are actually attached here. So we are getting this thing, and then in the reaction 3, we are getting here we are getting the ketone. Okay, so this is actually the oxidation. So if we look at this, if we break this bond in the presence of acidified potassium permanganate, which is the oxidizing agent, and this part will be changed into this, and the another part is this, because by the oxidation of C double bond O having two links, that is C double bond O having C double bond C having two links or two carbon attached, that is oxidized to ketone in the presence of acidified KMnO4. And if we have CH double bond, this is C double bond, this is CH double bond. So CH double bond is oxidized to carboxylic acid. So here the G is CH3, C double bond OOH. This is ethanoic acid. Okay, now J and G. Now we know that the G is ethanoic acid, so this part is from ethanoic acid. So if we split this part, we will get the G, or G is this part. It means that the rest of the part is of alcohol. Yes, we can break this bond from here. If we break this bond from here, we will get the rest of the compound. Like we will get so these two compounds, this is the J and this is the G, they will react with each other to form ester linkage. This is the alcohol, tertiary alcohol, and this is carboxylic acid. Now just look at the questions. Reaction 1, C2E, HBr gas, okay. Now the reaction 2 is E2J. Now E2J is E2J, okay. Now here, if we have Br and J is like alcohol, so halogenol alkane are showing the nucleophilic substitution. So we will use the aqueous solution of sodium hydroxide. Now C2G plus this. C2G plus this is, we have already explained that C2G plus this is the oxidation, and this oxidation will be done by hot and concentrated KMnO4, hot and concentrated KMnO4. G plus G to H. Now J plus G is esterification, and esterification is done in the presence of concentrated sulfuric acid. Okay, I think this was the last question. Yeah, I hope that you people will be able to understand this paper very well. And don't forget to subscribe my channel. So if you subscribe, you will get the latest papers. Thank you very much.